Welcome to Sundar's lecture. This is lecture number 29, and in this lecture we are going to see methods to avoid race around condition in JK flip-flops, right? So what are all the topics we have seen in the previous class? See, we have started with the excitation table for all the flip-flops. We have derived the excitation table for all the flip-flops by using the truth table, right? So we have drawn the state diagram. From the state diagram, we have just written the excitation table, right? So, and I've told you this excitation table will help you in converting one flip-flop to another flip-flop. Day by day, I'm saying this characteristic equation and this excitation table is very important. Be very careful while listening to these classes, right? So, then we have seen all the flip-flops, and we have also concluded this one, right? So, what is raise around condition in JK flip-flop? It is very simple to understand. For example, we have taken an example here with the graph. See, we have taken here at this point the level triggering. This occurs only in the level triggering, not in the edge triggering. So in level triggering, this is the high level. So we have considered it to be a positive level triggering. So at this stage, both J and K are 1 through the whole portion of the high level triggering, that means positive level triggering, the J and K values are 1, 1, that is high. So at that point, what happens here? The output will be toggling. It goes to 0, comes to 1, goes to 0, comes to 1, and then this point, after this clock pulse, there is a no change condition. Since there is no level trigger here, it is a no change condition, and this period, what is the value of Q, what should be the output of whether it is 1 or 0, that is a uncertain value. It cannot be exactly 1 or 0, that depends on the flip-flop's behavior, or it may depend on the propagation delay of the flip-flop, right? So there is a race condition here, and we are also facing a Q uncertain at this point. So this reflects in the next stage too, because this no change condition has to change from here also. You see J is equal to 0, K is equal to 0. So again there is a no change condition. So whatever the result we are getting here, that reflects on the next two stages. So we need to know, or we need to rectify this race condition so that the next stage output can be properly determined, right? So that is the case we have taken in the previous class, and we have explained this one. And in this class, we will see one by one how to avoid this raise around condition in JK flip-flop. For example, the first one we have taken it to be make flip-flop propagation delay greater than the pulse timing. For example, you see here, we have a pulse like this now, right? So we have a pulse like this. Let me draw this so that only you can easily understand. That is why I have not already drawn this one. This one, right? So you have a timing for this one, right? So this, let us take it to be delta t. For example, you may take anything it may be, but I am taking it to be delta t now. So for example, maybe we have to understand it be quite a nice way, so that I will take these stages. I will take these stages. So these are all the clock pulse stages. You assume this to be now level triggering, positive level triggering. For example, maybe I will straight away get it to this point. This is my J now. This is my J. It can be anything. I'm not going very deep. Anyhow, so this is my clock pulse. This is my J, and this is my K. K, that also I am getting high here at this point, and it may be anything. It can be anything, but we are going to concentrate on this one. This is now K. So Now the problem comes here. So this is now j is equal to 1 and k is equal to also 1. Right, whatever the output may be, I will draw the output in a different color. See, output is here. It may be anything. I am not going to consider at these point. Not consider. I am just going to consider from here to understand things, right? So what happens here? J is equal to k is equal to j is equal to and k is equal to 1. So there is a problem. So here you will have the propagation delay. Sorry, you will have a race around condition, right? So what is my point? I've already told you this timing, right? It is changing from 0 to 1. So again it is j is equal to 1, k is equal to 1. So it is coming from 1 to 0. Again j is equal to 1, k is equal to 1. It is going to 1. So there is a delay here. There is a timing here. This timing is a propagation delay, right? So for example, I will draw here. See here, there is a change like this. This is race condition, we know already, right? This is race condition. And what is this one? This period is the propagation delay. Propagation delay. Right? Now what I am going to do now? I am going to make this delay greater than the flip-flop. Sorry, greater than the pulse timing now. So for example, if j is equal to 1, k is equal to 1, so the flip-flop will take extra time, that means greater than this time. That maybe I will put this as now capital letter TP. So what I am now considering here, now TP is greater than the delta T. So what happens now? This will take another whole timing here. So again it will goes to 1. To process this output, if you take the whole time greater than this delta T, so what happens now? The race around can be eliminated, right? So this one, right? So this one, there is a different condition, so it can it will work in the next cycle. Maybe I've already told you in the propagation delay topic, right? So maybe this for this period it will work here, for this period it will work here. So maybe anyhow. Now we have just eliminated the race around condition. This is one way to reduce, one way to avoid the race around condition in the JK flip flop, right? So what is the next one now? Use edge triggered flip flop. What happens if the edge triggered flip flop is used now? Maybe I will draw the diagram. Right. Now you see here, I have just taken an example now. So this is a positive edge triggered flip flop now. So when the flip flop will check for J and K only at the positive edges. Can you understand? Only at the positive edges. For example, you see here, this at this positive edge, maybe I am assuming that there is a 0 in the previous state, and there is a positive edge here. J is equal to 0, K is equal to 0, so it will retain the same output until this point. Again it will check for the j k value, both are 0 again, so again it will be retaining at this stage until this point. And you see here, maybe we will take a different one, and okay, we have taken a different one now. See here, at this point, until this point, because here j is equal to 0, k is equal to 0, so from this to this point the output will be at 0 point. So now you see here, at this clock, at this positive edge, j is equal to 1, k is equal to 1. So at this stage what happens now? From 0 the output will toggle to 1, from 0 the output will toggle to 1, and it will be retained at 1 until this point. Try to understand. Until this point there is no change, because there is no positive edge are coming down in the clock pulse. But at this point j is equal to 0, k is equal to 0. So what is this one now? Since it is 1 here, the output will be retained again, no change condition. So the output can be again 1. Can you understand what is happening here? Because there is no time for the flip flop to stay at the j is equal to 1, k is equal to 1 at point. Since it will check at the next clock, positive edge of the clock, the race around conditions can be eliminated. So this is one type of avoiding the race around condition, right? Right. What is the next one now? It is master slave JK flip flop. Even if you are using the level triggering flip flop, you can avoid by using the master slave flip flop. Master slave JK flip flop. See here, this is one JK flip flop. This is another JK flip flop. Try to understand. But what we are doing now, we not another JK flip flop. Maybe you can take this as a SR flip flop because you are not getting the feedback, right? So you take this as a SR flip flop also, right? Master slave, master is JK and slave is a SR flip flop. You can avoid the raise around condition by using these type of design, right? So what we are actually doing, we are just giving the clock pulse to this flip flop. Maybe you take this as this point is now S and this point is now R, right? So what we are doing now, we are giving clock pulse to the JK flip flop as here directly, but we are just inverting this clock pulse and then we are giving to the SR flip flop. That is the connection, and we are taking the feedback from here to here, from here to here, normal as in the JK flip flop, but we are taking it in a different place, right? So now what happens here? See, at this stage, the clock pulse is 0, so I am just assuming y is equal to 0 and then q is equal to 0 in the previous state. So I am just taking like this now. So for example, now since this is now 0, this output is 0, this is now 1, right? You know this one. So what happens now at this point, the clock pulse is 1 here. So this clock pulse is 1, this clock pulse is 1, this clock pulse is 0, this clock pulse is 0. What I have assumed already, this to be 0 and obviously this to be the output here it is 0 and here it is 1 already, right, in the previous state. So now it is coming to 1. So here this one will go here. So this flip flop will get 1 here from here and this flip flop will get 0. This flip flop will get 0. Now what I am actually going to do now. So I am just going to give this j is equal to 1 and then k is equal to 1. So what happens now? This j is equal to 1 now, k is equal to 1 and clock pulse is 1 here. So what will happen? Whatever the previous state you have here, that will be inverted now. That will be inverted. So what I will get here? So straight away I will get a 1 here. Can you understand? Can you understand? This is 1, right? So this will converted to 1 now. So obviously this will be changed to 0. And this is 1 means this one will go 0 here. This clock pulse is 0 now. If this clock pulse is 0, if SR flip flop don't get a clock pulse, then what it will do? It will be retain the previous stage. It always try to retain the previous stage. Am I right or wrong? Right? So what happens now? This flip flop output, that means Q will be 0. Will be 0 now. So now what happens now? I am giving 0 here. I am giving 0 for the clock pulse. So this clock pulse has changed to 0 now. So this will change to 1 simply. Am I right or wrong? Right? So if this is 0, then what is the condition of the JK flip flop if I am giving clock pulse as 0? Simply the previous state will be retained. What is the previous state? It is already in 1. Y is actually JK flip flop, Q is actually SR flip flop. Try to understand. So this one will be again retained. Here. So this one will be again retained here. Right? So what happens here? Since this is 1 now, S is getting 1 here because this is 1. This 1 is connected to this point. So S is getting 1 and this 0 is connected to this point. So R getting 0. So S is equal to 1. R is equal to 0. What is this condition? What is this condition? It is a set condition, right? Set condition. Try to understand. So SR flip-flop is getting a set condition and the clock pulse is also 1 here. So what happens here? What happens here? This clock pulse, this output will be 1. Will change because this is going to be 1 now. So this one will be here. And now I'm just going to change the 0 to 1 here. So if this is 1, this is going to become now 0. Right? If this is 1 means what will do? Already j is equal to 1, k is equal to 1, and whatever the input, whatever the output is already there, it will be converted to 0 now. This y. So this y is already 1 here. What will happen here? This will be converted to 0. So this will be now 0. But if this is 0, this clock pulse is already become 0. Right? It is already 0. So if it is 0, then what happens now? This SR flip-flop will retain the previous stage, right? So this will retain the previous stage. That means this will be 1 again. Right? So now what happens now? This becomes 0. So this becomes 0, then the clock pulse is here, it is 0, here it is 0. So if JK flip-flop clock pulses become 0, then this will retain the same state. But what happens here? This output will become it is already high. This is already in 0. So now this 0 will give will make this SR flip-flop to, because this clock pulse is 1 here. This is now S is equal to, we will get a 0 here. What is S is equal to 0? R is equal to 1 condition. It is a reset condition, right? It is a reset condition. So what happens now? This will come to 0. This will come to 0. Try to understand. Then it will be continuing like this. So this will goes to 1 and this will be retaining here. So what is happening here? The output of the flip-flop is actually inverting. See here, output of the flip-flop is inverting, right? That is what we just need, right? J is equal to 1, k is equal to 1. Then what should be the output? The output should be changing from 0 to 1 and 1 to 0. That is the real expectation from a JK flip-flop. That is actually happening here. See here, 0, it is going to 1, it is coming to 0, and it is again going to 1. But what we have avoided here, we have just avoided the raise around conditions. That means there is no place the output of the flip-flop is going like this, with uncertainty, with uncertain output to the next state. It is not happening over here. Try to understand, right? So if you are listening to me for the first time, for this one, it will be confusing. Please repeat my video to understand this one. Then only you can easily understand this concept, right? So you can just straight away say that if I put a SR flip-flop in series with the JK flip-flop, and if I give the feedback of the SR flip-flop to the JK flip-flop, I can avoid the razor on condition, but I will get the toggling output if I give J is equal to 1, K is equal to 1. You can say that, but if you want to understand this one clearly, then you need to be very careful, right? So this is how you can avoid the raise around conditions in the JK flip-flop. So what are the topics we have seen in this class? See, we have started with the methods to avoid the raise around condition, and we have seen how to avoid the raise around condition by making the flip-flop propagation delay higher than the clock pulse timing, right? And then the second one, it is very simple. Use edge triggered flip-flop so that you can avoid the raise around condition, and also you can go for master slave JK flip-flop or master JK slave SR flip-flop. You can avoid the raise around condition, right? So we will see conversion of flip-flop in the next class because that is a new topic, so that we will start it in the next class, not in this class, so that you can easily get a continuation over there, right?